Since continuity's definition is derived from limits, those laws of limits apply to continuous functions. So if you have two continuous functions, their sum and difference is a continuous function. I can multiply a continuous function by a constant, and that's still continuous. Their product and their quotient are continuous as long as the function g is not equal to 0 at a certain number. So remember all those functions that you covered in pre-calculus that are continuous in their domains. So again, we'll look at a piecewise function. Is this function continuous at x equals 0? Well, you need to check the endpoints of these domains defined in the piecewise function. So cosine of x is continuous everywhere, and 1 minus x squared is continuous everywhere. So let's look at what's happening. So as x is less than 0, and x is approaching 0 from the left, that means that the limit is going to be approaching 1. The y values will be approaching 1 because cosine of 0 is 1. However, the function definition at 0 is equal to 0, not 1. So this is discontinuous from the left. Now if you look at these two parts, as x is approaching 0 from the right, it's using this function, so it's approaching 1. However, x of 0 is not 1, it's 0. So it is not continuous at x equals 0. Let's look at this example, this rational function. Determine if it has any discontinuities, and if it does, classify them. Well, the first thing you're going to want to do is factor the numerator and denominator to see if you have any common factors, to see if you have any wholes. And then you want to look at the zeros of the denominator, if there are any others. So when we factor the difference of two cubes in the numerator and the difference of two squares in the denominator, we see that x minus 2 is a factor that's common to both the numerator and denominator. So x equals 2 is a whole. So we have one removable discontinuity. And then x equals minus 2 is a 0 of the denominator we see from this factor. So that's going to be a vertical asymptote. So there's going to be a whole at x equals 2, which is removable, and there's going to be a vertical asymptote at x equals minus 2, which is an infinite discontinuity. So this theorem is telling us that the composition of two continuous functions is continuous. And you've actually seen that in section 2.3 when we were allowed to put the limit symbol inside of a function, if you recall. So let's take a look at this. This is a handy theorem. So we're going to use continuity to evaluate this limit. And we're going to use that theorem that we just saw, that the composition of two continuous functions is continuous. So let's look at the inside function of this composition. This is a rational function, and it's defined for all x, since x to the fourth is always positive. It's never going to be negative 1, so that we're never going to have a 0 in our denominator. And so we know it's continuous everywhere. Now the outside function is the square root of x, and we know that that's continuous for all x greater than 0. We can only put values of x greater than or equal to 0 in that. And notice also that this rational function is greater than or equal to 0 everywhere. So each of these functions, the inside function and the outside function, is continuous, so their composition is continuous everywhere. So that means that the limit as x approaches 1 of this function must actually equal f of 1, because that's the definition of continuity. So since we know it's continuous, we can evaluate the limit by just plugging in f of 1. We're plugging 1 into the function, and we get the square root of 1/2. Here's another example that I'll leave to you. With piecewise functions, you want to look at each individual function, and then you want to look at the endpoints to see if your limits work out from the right and the left.